good morning, everyone. I'm James Stark. I'm a postdoc at the PSFC as well. I'll be continuing on from Remy's talk and talking about some applications that we try to use FESTIM to model different types of components around the fuel cycle and the problems we've been running into doing that. So yeah, as he noted, there's a few different components that we want to be able to model because fusion reactors for the moment are not real, so we need to help design different analysis techniques to help in the R&D of the different components that we want to have. For instance, the diverter at the bottom of the reactor, the breeding blanket that will surround the plasma vessel, as well as a whole bunch of different components in the outer fuel cycle, such as different tritium extraction systems or general hydrogen extraction systems, and heat exchangers like the nice GIF before. But in many of these different components, tritium is not only just diffusing through different domains, it's also being carried because it's being dissolved within a different fluid, whether it's like a liquid metal or a molten salt. So we need to be able to model these different systems. We thought in theory you just add this little advection term and then you're off to the races, it's all good. And yeah, I guess in the title I originally had, this is where FEM struggles, but actually it's just where non-FEM experts, comme moi, struggle. So this was an effort into trying to design a proper DG method for this. Because yes, generally a lot of stuff that we do in FESTIM is just kind of bog standard CG1 methods, and this is where it's very difficult to do any kind of advection diffusion stuff. The main issues that we were running into was just getting any kind of like mass conservation at a global level. We were often getting more tritium being extracted than was ever generated, or so this is when we then realized we had to kind of go back to the drawing board and try and figure out how to do things properly, which is where, after speaking with Joe, realizing that we should probably be doing things with DG methods, because then we can get flux conservation on a kind of cell-by-cell basis and a bit more stability overall. So yeah, so we should have been doing it like this all along. But the actual formulation itself is not insanely complicated for now. I don't know. Let's see how we get on. So we have our bulk diffusion, bulk advection term across the cells. We then have our interior upwind flux terms, helping enforce the direction of from the flow. We then have our bulk diffusion term, as well as some SIPG diffusion across the different interfaces as well. I actually made a little kind of online book thing, kind of detailing my journey into this, a mild introduction to suffering, I called it, where we basically started off just with some a nice simple kind of example just of an MMS, kind of starting off with manufactured solutions to actually just make sure that we've implemented this thing properly and that it scales well, and then kind of building up in complexity closer to what we actually want to model. So going through like a pipe model up to Stokes flow in a box, and then coupling with other engineering software that we want to use, like OpenFOAM, for instance. So yeah, so if you're interested in that, please check it out, and you see anything wrong, please add a PR, sorry, to help me correct that. But yeah, so all in all, so we did some manufactured solutions just to ensure that actually our problem is scaling properly and showing that in advection-dominated scenarios that we should be scaling with HP plus 0.5. And things seem to be working out all right for now. But yes, as I mentioned before, everything is, you can verify everything works quite nicely when using analytical velocity fields, but actually when we're designing these engineering components, we need to use real velocity fields of real components, and so we're trying to use more commercial, well, more widely used software like OpenFOAM. So we developed a small package to be able to read the velocity fields from OpenFOAM called Foam to FEniCS. This is it here. I know that there are other software out there that's designed, I forget what it's called, for coupling with OpenFOAM, but this one was more for like coupling surfaces, whereas in our case, we really needed the bulk fields to be able to couple to model the advection effects on the tritium within the fluid itself. But this is what it looks like. So you can read any kind of foam case file like this, and then you can pick out any of the fields that OpenFOAM produces, whether that's the velocity field or the temperature field or anything else. We can then extract the mesh, and we can create FEniCS mesh tags from the data that's in the OpenFOAM file. And then once you have all that data, you can then save it to a checkpointing file using packages like what Jürgen made, IO to FEniCS. But yes, in this multiphysics model, like Remy kind of touched on, there's lots of different physics that we need to encompass, including stuff from neutronics, which is OpenMC is a open source Monte Carlo stochastic code for modeling radiation transport. This basically gives us several different things, such as nuclear heating terms, which is then fed into the CFD software to account for the thermomechanical effects. It also gives us our tritium generation term. It just tells us where all the tritium is born across the different, across the blanket system in this case. And then from OpenFOAM, we can get all sorts of things like the temperature, velocity fields, and also turbulent viscosity, because again, it's another form of diffusion that we can account for, which is the additional diffusion due to the turbulence inside the fluid as well. And then for this model in particular, we actually have a kind of like inner ring and an outer ring in a sense. So in the inner ring, our inlet of the molten salt's kind of coming in through here. It's flowing around the inside, and there's actually a little interconnect here. And then all the fluid kind of goes back up around the outside and out the outlet at the top here. So these are the kind of results that we get from OpenMC that we want to port in, which is our nuclear heating and tritium production rates. And then once the nuclear heating is ported into into OpenFOAM, these are the kind of results that we get from there. So we have our turbulent viscosity fields, our velocity fields, and the temperature field across the whole domain. And all of this is then passed into FESTIM, where we can then do our advection diffusion to figure out where all this tritium is being born and where is it going. And these are the kind of results that we can get. And then from this result, we can then figure out where these different hotspots of tritium are. So where is it gathering and why? Because this is obviously important from a safety point of view. We want to figure out where the hotspots are. Where is it then diffusing into walls, for instance? We can also then look at transients. And in this case, it's from doing all this multi-physics work that helps us kind of refine the design of these different components. Because for instance here, what we're seeing is on the top kind of two segments here, we're getting a lot of recirculation, which is then in turn causing a lot of turbulence, which then helps kind of spread the tritium out so you don't get as much of a hotspot compared to this zone here where we actually just get a lot of stagnation in the flow. And so because it's not moving very much, the tritium then just kind of gets stuck there and isn't kind of diffusing out. So it's in these types of workflows that we'd be able to help kind of design these components to make sure that we can extract as much of the tritium that's being generated in this component as possible and as quickly as possible. And so from FESTIM, we can obtain values like the values of these max concentrations here. We can also do some transient analysis to figure out like how long it takes to get up to a point of steady state. And we can also extract certain things like the amount of tritium that's being pulled out the outlet, as well as the total inventory as well. I should also note that, so this model is about, I think it's 1.4 million cells or so. The steady state simulations took about 20 minutes, and this transient took a few hours, although we had a very nice talk from Jack yesterday showing how things should be done properly in parallel, and I wasn't doing that, so hopefully in future it will be a bit faster. But yeah. And so yeah, these are the kind of like engineering outcomes that we want to be able to extract from these types of workflows and these values. And so yeah, so in conclusion, we developed a DG advection diffusion solver for hydrogen transport that we want to integrate into FESTIM. However, there's lots of work that can still be done. We want to look at alternate formulations as well, such as skew symmetric methods, or I know it's similar. There's also been some other advection diffusion stuff where you guys have methods that don't include the penalty terms. So we might want to look into that as well to kind of make things a bit easier for our users. And also extending these models to be multi-material models to then account for any diffusion into exterior structures, as well as better time discretization methods as well to avoid any artificial diffusion due to that as well. So yeah, thank you very much.
Thank you very much. Very interesting. Any questions from the audience? Yep.
If you go one slide back, so I saw the concentration here being at the scale of 10 to 20.
Yes.
Why is it here not in moles?
It could be.
How careful are you when it comes to the big and the small numbers in the model?
Yeah, as long as we're controlling our absolute tolerances, that's usually fine. But we have talked with Jürgen a lot about having to it might be better to scale down our problem quite a lot to kind of make the solving a bit easier. But yeah, because we tried to just do everything in SI and just do it in, so this is in tritium concentration per meter cubed. But yes, we could scale down to moles, and that might make things a lot easier as well. But yes, something we thought about.
Other questions? Yep.
Since you are going to use OpenFOAM for CFD, and OpenFOAM is able to do advection diffusion,
Yep.
what not do everything in OpenFOAM?
Yeah, what's the benefit? Yeah, so the benefit is then when we go on to more multi-material systems. So when we can then account for diffusion into the structural walls, and then we can account for all the different effects there. It's like getting trapped in the walls and the different surface reactions that are happening, and particularly the interface conditions between the different materials. That's something that would be extremely painful to do in OpenFOAM. So yes, if you're just looking at the fluid, there's no point doing this. You may as well just do passive scalar transport in OpenFOAM, but it's for when we move on to more multi-material systems and we want to see where it's diffusing out and the effects then, that's when FESTIM will come into its own.
Yep.
Did you build the OpenFOAM reader from scratch, or did you build on top of ETJ or PyVista?
It's built on top of PyVista. Yeah, the OpenFOAM reader in PyVista.
So maybe I can take the opportunity. So again, in the afternoon, I will present. So you say you don't want to do CFD and so on, but what I will present, I think CFD is very simple and sort of turbulence.
You might be one of the few.
So maybe that could be a proposal from me. Why not try to do that? And it should be sort of Newton's law, F equals to ma. That's quite simple, right? So in principle, that should be it. And then all these issues like transferring things and what you're saying, this should you do something in OpenFOAM or not, and so on.
Yeah, we know.
And,
yeah.
But maybe what's your perspective on that? Wouldn't you get more control if you could do everything sort of in FEniCS and you do everything yourself?
Absolutely. No, I think there's a lot to be said for if we could do CFD in FEniCS. Because I know we have been having a lot of issues. Like, for instance, as soon as you try and interpolate results from OpenFOAM into any kind of mesh in FEniCS, you are losing some data that way. Or actually, the issues we were having initially were we were just kind of naively interpolating it into a CG space, which then kind of lost all the divergence-free nature of the solution you get from OpenFOAM. So that's something we've been dealing with. So yeah, in a perfect world, it would be much better to do everything in FEniCS and then have everything coupled in memory as well. But thankfully, from our perspective, because everything influences hydrogen transport, but hydrogen transport doesn't influence anything else. We don't need strong coupling, so weak coupling is fine. And for us, like Remy said, we're not CFD experts. I personally tried to build a little CFD solver in my PhD, and at first things are very nice, and then it gets very complicated very quickly. So I quickly abandoned that, and because using these tools where all the turbulence models are already built in and verified and well made and scale well, we prefer to use those. But we're absolutely open to using FEniCS alternatives as well. It would certainly make our lives easier.
Great, thank you. Any other questions? Otherwise, maybe we thank you again and move to the next speaker.
Thank you.